Welcome. My name is Nils Thürey and I'm back for a recording from a lab at TUM. We've been focusing on some in-person things for a while, but now I would like to get back to recording some online videos, and this one is a special or especially important topic, I believe, focusing on unrolling, so how to couple your simulations with deep learning and some of the more subtle aspects that nonetheless are really important. So here we go. Let me start with a somewhat more generic outlook. We're facing countless challenges as humanity, and numerical simulations, I think, are super important. We have a really powerful toolbox here that we want to keep. Now we have the new techniques in form of deep learning. How do we integrate that? That's one of the key challenges for many of the research topics in that area. As mentioned, I want to look at unrolling and simulators here today, and for that, let's look at our solver, given in the form of a PDE, as this function f shown here at the top. So we have f depending on a lot of derivatives, giving us the time update without loss of generality. We could extend this to higher order solvers, so now let's keep it with this formulation. And we have a series of ground truth states from u tilde 1 to some large n that we want to obtain. So that's our target, u tilde. Now, to start with something super simple, let's approximate the time stepping here. So that's the ut plus 1 that you see here. That's what we like to get. We have some function g. I'll come to that in a moment. Potentially that is a deep neural network, but we'll look at some variation of that in a moment. And given the ut, we now want to obtain the next one, and this ut plus 1 should now match as closely as possible the ground truth given with the utility. And just to make it really clear, here this could come out of any solver. This could intentionally, don't want to focus on any details of the architecture. This could be a GraphNet, ConvNet, MLT, whatever is your favorite architecture basically. So down here I've shown a non-trivial mesh to highlight that a bit, but we're looking at an operator perspective now. So given the solution at one point here, the black dot, this goes into our G, and out should come the next time step of that U at that location, and then we're running that over the whole grid wherever our discretization tells us we should go with our solve. So that's the basic setup. As a loss, in most cases, actually, I'll just assume we have L2 here, but likewise, we could extend this towards other loss formulations. So this is our basic setup. Now, from this operator learning perspective, let's consider our PDE as a chaotic system. So, also, I want to look at any neural network architecture, and we would like to now approximate this chaotic system, which converges to certain stable states, the attractors of our chaotic system. And we'd like to do this now having a simulator, and in certain situations also not having a simulator. So I would like to, in the following, distinguish two fundamental and different learning tasks for this. One is what we've looked at the past quite a bit, what you could call a correction task. So we're using P, but P doesn't directly give us the perfect solution. It's an approximation, giving us a partial step towards the ground truth, the utility from before. And the rest, the residual, that's what we'd like to learn. So this gives a hybrid simulator as outlined here, and if we write it up, it's basically we apply our simulation operator P to the solution, and afterwards we call a neural network f of theta, parameterized by the weights, and together P and F then form the corrector G. But yeah, this is just one way to look at it. So to really make it clear, in this case, we basically alternate calling P and then F to give us a solution as shown here in the box. You could actually swap those. It's a matter of definition and potentially also parallel, but those are subtleties. So key point being they're working together. This contrasts with what you could call a pure prediction or pure neural surrogate, where G basically only consists of the F only the neural network. This means, or you could think of this as P being the identity function, then the picture still holds, but P basically doesn't do anything. So in this case, it's really up to the neural network, the F, to do everything. But let's look at both of them together. So as an outlook, I want to consider both correction and prediction tasks. Now, from the F, from our original PDE formulation, we have a certain attractor that provides a ground truth. And now, in the simplest case, given the goal we just had on the previous slide, we could just learn this. We could basically collect a lot of data, big data set, and then minimize L2 loss between the utility T+1 and the output of G. Right? That's what you could call a supervised approach. Now, that's of course a good starting point, worth trying, but unfortunately, can show quite easily that our F will not be perfect. Right? We're approximating utility, but in most cases we will not perfectly get there. There might be a tiny residual error, and if we look at this time stepping, this chaotic system perspective, then this error will accumulate. And a key problem with this learning task is that at training time, we're always just looking going from UT to T+1, which means the iterative application of our F, potentially this infinite series of applying F, the learned F especially, as part of our G, will not actually be seen at training time. So if you write this up, to formalize it a bit, for all ground truth states from our ground truth attractor AF, we get an attractor of this G that will not really match the true one as we increase the length of that chain towards the capital N. So basically, the more steps we do, the less our one-step approximation will potentially expose what this G really does, right? Because we're basically not seeing how these errors accumulate and then drift away from what we see with individual steps. So what can we do about this? Probably already thinking, well, obviously we need to consider more steps, right? We're just looking at one. Let's do more. You can consider this as unrolling, and here's a nice generative image that illustrates this unrolling process, indicating we need to go backward and forward. We have a long chain here. Now, these multiple applications of our G will now be denoted by this lowercase m as indicating multiple steps of unrolling. And if we now do this, especially if the m gets large enough, we really can expose the attractor of this learned G at training time. So as m goes to infinity, at some point we're really unrolling the whole chain, and this shows the true nature of what we learned with G for training. And now if we minimize the difference between this AG and our ground truth AF, we can actually train the correct thing, also the long-term perspective. So mind you, of course, there's a caveat here. We have an infinity. This only holds for infinitely long sequences, which is slightly impractical. So we need to do something about it. I'll get back to it in a moment. So another subtlety that doesn't show up here directly, but if you think about it, we're applying this G multiple times. We want to learn with this, which means we actually need to backpropagate through all these calls of m, these iterative or autoregressive calls, as you might want to call them, which requires us to backpropagate through the whole G, and G might contain the simulator P, our physics simulator. So this actually means if we want to do this correctly, we need a differentiable simulator. We need to be able to obtain the derivative of that P with respect to its input, the U. This might not always be around, right? So some of you might now be tearing their heads out. You know, I have a 70s Fortran code, it doesn't have a derivative, right? So this is actually comments we got quite a few times. And yeah, the main point here for now is, if you look at this from a chaotic systems perspective, as we go to infinity for m, we can actually really make this converge and learn the real attractor, but might be tricky because we require this differentiable simulator. So one of the key messages I already want to give away for later on. If you don't have this, it's still worth considering. So I'll come back to that in a moment. Or to take it away, basically one of the key messages I want to make in the following is, even if you don't have the derivative, putting your solver in the training loop is a crucial step for training. But right, for now, let's look at this correct setup where we have the solver with the derivative, and we can really unroll and backpropagate through the whole chain. Now, so far, it probably sounds like this solves all of our problems. So here's a nice image to illustrate the problems with this. What we're actually facing, even when we're doing this, or as we're doing this, is a classic data shift problem. This nice image here illustrates it a bit. You can imagine we're training on the blue side with some training data, and then as we apply this method in real-world cases, in this case, especially the autoregressive part of it, will make our data different. That's the accumulation of the errors that I just mentioned. So suddenly we have some colors in there, and if we put these into our network that was never trained on seeing any colors, it might go wild. So we might get arbitrary errors out of this, and these sides of the shift along the unrolling nicely illustrate that. So for machine learning, that's a classic problem, and what I've shown you so far with the unrolling kind of implies, well, that's especially a problem if we train this one step and then we want to do many, right? Then we have a huge difference between what our data looks like and potentially what our real world data later on looks like, because the data basically doesn't have any influence over the network of the F, whereas if we apply it, the F will play potentially a huge part, and in the worst case, destroy all gains, all accuracy that we have and that we would like to obtain by training F. So, as before, first sight, the unrolling seems like it would solve all this, right? As we unroll to infinity or many steps, potentially we can actually see the whole effect of this, which sounds like we could just do this and then make sure we essentially don't have any data shift. So what we have recently looked at, and what also has been investigated by other people, is that this unrolling actually does introduce problems. So we actually are typically approximating this direction of the step with Jacobians, with linear approximations, and we apply those for each of the steps along the chain. So we will actually see over the course of the unrolling a divergence of the gradient from our true dynamics. So that's nicely illustrated now at the bottom here with this orange curve. And if we now also look at the equations behind that, what you actually get for the one-step training is just the derivative of our loss on the top left, our L2 with respect to the network, and the network with respect to parameters. So that's essentially two Jacobians. It's a classic Jacobian vector product that you see in deep learning, and this is our F might be non-trivial, so this, despite the shortness, is not easy, but when we unroll this, we get something that's a lot more complicated. So for these formulations here, we actually get something that depends on the current length of a chain. So if you just consider a single unrolled chain towards a step in the equation on the right S, we actually backpropagate this through the whole chain back to the beginning for one input. But then we do the same for the next one. So for the next one, you get actually S minus 1 to the beginning and S minus 2 to the beginning. And all of these are summed up. So essentially, if we're looking at something triangular, something quadratic in these terms, each of them potentially an approximation and potentially a Jacobian matrix with some unstable modes. Yes, there might be something in these Jacobians which might lead to a blow up of structures in a solution. And suddenly you had to basically quadratically applying these matrices and reinforcing those modes. So if there's anything that blows up in these Jacobians, just as an intuition, that can cause trouble. Now, in some papers, we actually also looked at the underlying loss landscape. And it's really interesting to see how that behaves. So this is now from a paper by Patrick, iClear22, and we've looked at a super simple polynomial. So our solver here now is just a quadratic polynomial that you see up here. 2 degrees of freedom, so we can plot the whole loss landscape for certain coefficients. You already see this on the left here, looks very boring. You can see a slight shade of this quadratic function here, so it's increasing towards the top left corner, and derivative is just linear, so we see these slanted directions on the right hand side. So far, so boring. But now let's look at what happens if we unroll this very simple function. We do a single step of unrolling, so just applying this simulator twice, and suddenly we have up to 4th order terms, and now things start to get interesting. So we're starting to see a kind of valley, a clear minimum region at the bottom right of the loss landscape, and the gradient field now also becomes much more interesting. So potentially this region was chosen to show some interesting effects. So the gradient in the background actually shows the magnitude of the gradients. The arrows just indicate the direction, and there's this horizontal dark line that you see that this indicates a saddle point. So already region doesn't look interesting on the left in the loss landscape, but where the gradients go to 0. So we are learning would potentially really stagnate and stop because this is a saddle point, right? So of course have momentum in other terms, but indicates just with 1 step things start to be more complicated, and now we go to 3, 4, and this is 6 steps now. And we can see a bit now, right? The loss landscape actually has all these tiny curved minima regions. Those are actually the ones we'd like to reach, right? This is where we want our optimization to go. And on the right see we have now a huge central saddle point region where our learning would stagnate, and on the sides it's super steep. So after a few steps unrolling, difficult things easily happen, and that's what is nicely visualized in these plots. So this is something we need to deal with. And to connect it to the previous graph, right, this is this kind of explosion that we see. Potentially we are dealing with very higher order terms and difficult to navigate loss landscapes. One other topic that I want to, from the beginning, now connect to the current state here is a bit, we're looking at these different tasks. I've mentioned correction and prediction so far, but I would like to encourage you to keep in mind that this is actually a continuous base of different tasks. So the involvement of the simulator could vary, and it could take different roles. In the extreme case, which here is actually shown in the far right, so down there, the simulator does a perfect job. Great, nothing left to do for any other learned system or so, but usually that's not the case, right? Our simulator usually is not perfect. The other extreme now is the simulator does not help at all, or we don't have any description of what our system is supposed to do, and we can only rely on data and our neural network. So that means this pure prediction, it's the other extreme, right? Pure solver before, now pure network surrogate prediction, only the recurrent neural network happening. And nonetheless, we have this whole space in between. It's obvious where I'm going with this, right? So now in between these two, we have all these different correction tasks. And here the solver can play a smaller or larger role, and the rest is taken care of by the neural network. And even if it might seem you have some simulator, right, some legacy code that does the job, often there is a chance for varying this, right? So especially towards the right side here, you could imagine this happening as you increase resolution, all solver convergence thresholds, right? This might be super expensive, but often you can dial those down. You can choose a coarser spatial discretization, you can reduce accuracy thresholds, you can make larger time steps. All of these will speed up the solver and move you closer and closer to the left side. And this is a very interesting degree of freedom that you have to set up the learning tasks. So actually I would encourage to do exactly this, to start with a coarse solve, a fast one, and then add a network. So be somewhere maybe in the middle roughly of this continuous space. As I'll show in a moment, this is I think the truly interesting applications of deep learning methods lie. But important is that this is a whole continuous space. Now, I've mentioned this gradient flow before, and here's a nice example from our corresponding paper that shows how this works. Now, first a single step, right on the left we have the very first initialization, some step I in this case with state utility I. That goes into a solver P into the network to produce a UT+1, and then we have our utility T+1, and we can compute a loss. That's a simple case, we just backpropagate in network. That's a simple single step supervised case. Now we make a second step, things become more interesting. Now this output of the network goes into the solver again, into the network again to produce UI+2 in this case. We have a reference utility, can compute another loss, but this loss now goes into the network twice already, right? It's going into the F. We have last a second call to produce a gradient for our weights. Then it will continue in the backpropagation chain, the orange arrows at the top, into our first call of the network. And if you count now, we have one network update from the first call of our network, and then two additional ones from the unrolling chain with the second step. So unrolling 2 times will already give us one update from the second step and 2 updates for the first invocation of a network. 3 in total. They're typically just additively accumulated over the unrolling chain, and then if you imagine it, do another step of unrolling, suddenly we have 3 additional network updates, gradient for our theta here, and all of these would be accumulated on top. And this is where the quadratic nature of these updates come from, right? These potentially superlinear exploding components of our solutions. Now, this is a correction case. We have the solver and the network. To put this side by side, the prediction is slightly simpler, but not really different, as I hope this image conveys. It's just the P doesn't do anything. It's our identity, so we can drop it out of the picture, but we nonetheless have the same chain of network applications and the same number of gradients, so it's really very, very similar. Now let's look at what this does in practice. We've actually looked at the full picture, these fully unrolled chains of training with differentiable simulators in a variety of previous work over quite a few years by now. That's an example from a solver in the loop paper. Looked at this for turbulence, control, chemical reaction, also plasma simulations recently. So this really works very nicely overall. But we always made sure that we had the simulator with differentiability in place, often spending quite some effort to produce this. I want to show one example from this. So here's a turbulence mixing layer case from a turbulence JFM paper. You can see this as learning, this correction step as learning a closure model, essentially for turbulence, that both takes care of the turbulence closure and the numerical errors that our solver makes. And this being a very classic case, you can evaluate this with respect to all the classic metrics. The energy spectrum is the first indicator, so the ground truths are these orange dots. The pure solver, P only if you want, has a output that produces the blue line here, so it's definitely too low. And the 3 green ones are different learned variants here. So in this energy spectrum, it's actually very aggregated, doesn't show so much, but if you look at different losses, here's another one. These are downstream Reynolds stresses that indicate the amount of mixing happening across a cross-section of our flow. Now the differences start to show more clearly, and the blue line is again suboptimal. The 2 green, dark green models overshoot towards the top. They learn something, but actually they might go too far if you want. And the light green one, that is actually quite close to the green, the ground truth. In this case, that was really a full solver being unrolled for 60 steps, which is close to the kind of characteristic length of the underlying physical phenomena, which is actually a good way to estimate the amount of unrolling that makes sense. And this turns out to work real nicely. So based on this, we can now also make really a hard comparison. We can lower the accuracy of the reference solver to be on the level of our neural network, and then compare the performance. So we did this for this case, and saw a speed up of more than 10, which I think is quite encouraging. I'm also aware that this is not like the hundreds or thousand times factors that other papers reported, but I want to caution this is really a fair comparison here. The solver runs on the same hardware with the same optimization as the neural network, and the accuracy actually reduced with some of these other factors. I would be cautious, or it's worth double checking what is really compared here. Nonetheless, I think this hard comparison is still encouraging. Even if you would spend a lot of effort on your solver, the network is actually still able to outperform, thanks to its specialization, potentially the reference solver itself. Yeah, so in a way, the main message here also for us was this works quite nicely, but this is now all trained for 60 steps with the whole differentiable solver. So this is producing really the correct gradients along the whole chain of unrolling, and also we needed to do a curriculum here, so this learning needs to be built up from 1 to, this case, 5, 10, 30, 60 steps to keep this gradient divergence explosion from overtaking the learning. And now, of course, the question is what happens if we don't have this gradient? Because many solvers actually do not produce this, and rewriting them would be a huge effort. So this is the same picture from before with the whole chain. If we now think about what happens if we don't have a gradient from our simulator P, well, this is only used one time here, right? In the center, one time we backpropagate through P back to ut minus 1. If our solver doesn't have this, right, basically a whole computational graph for the backpropagation shortens. And what we're left with is this graph. So now we have the light blue arrows instead, which only go from the loss into the previous network call. So as you can see, especially as this is unrolled more and more, we're dealing with less and less of these repeated chains through the early stages of our network. And one of the key things here is actually that we're making an error. Before I had the correct solution with the repeated backpropagations. Now we're dealing with something that still depends on the number of steps S in the equation, but it loses this quadratic nature. And instead what we're left with here is something that grows linearly with the number of steps. And knowing that the true solution is actually this quadratic formula, we're now making an error. That is what's shown here with the blue curve. The gradient divergence due to this additional error, the lacking terms, potentially is larger than what we had with the full orange curve. But nonetheless, if you look at the picture here, we still have potentially a sweet spot where the data shift is reduced from unrolling, and the errors we're making from the gradient divergence are not yet overtaking or drowning out our actual learning signal for the neural network. And this is potentially still worth finding. So we're now dealing with the divergence here between these two, but the big question is, well, it's worse, but how much worse? Can it still work well in practice? And to be short, yes, it can. That's what I want to show in the following. So we looked at this first for a simpler problem, at a chaotic Koromoto-Zivoshinsky equation, one of these turbulent flame fronts, different domain resolutions to bit in line with generalization towards different Reynolds numbers for fluids. And here now are different results for a graph net on a one-dimensional case problem for these three variants: the simple supervised one-step version, the with gradient in orange, the correct version, and this truncated gradient in the following called NOG or no gradient version in blue here. And I hope you can already see there's, especially for the smaller networks, a clear transition from 1 over NOG to with gradient, becoming better. It's a log scale, by the way, so there are typically significant differences. And along X here, you can actually see different sizes of networks. So the left ones are tiny, 500 weights, where single layers up to 1 million, with on the order of 20, 30 layers, 1 million of weights, and right, this kind of network is crazy for a 1D problem. This is way over parameterized. Nonetheless, neural networks don't really overfit, as has been indicated recently, and it still becomes better and better, so there's no limit, right? So many weights do help, and in this cases, also the no gradient version potentially does not so good, but I would argue this region with the 1 million or even 200,000 is actually not so interesting for this tiny problem. We could solve the whole task numerically way more accurate, especially the middle region is interesting. And here we see substantial differences between these two methods. Now, here's another case where now we look at the same data set, but with a prediction task. So the previous one was a correction, lower order solve. The right side is no simulator anymore. And interestingly, in some cases, the no gradient version blue even outperforms, potentially due to the less strong backpropagation unrolling, the with gradient version. Both of them are better than the supervised variant. So again, across all these different sizes, the error is generally a bit larger for prediction because the network has to do more. On the left side for correction, the solver takes over producing a part of the solution. The right side, we can't rely on this. But if you're interested, we also looked at this for other problems, Kolmogorov flows and airfoil flows in our paper. But as a first indicator, there is actually a word of caution that I want to mention here. Also giving a pointer to this iClear paper that I mentioned. As soon as we do something like this removal of a gradient, essentially you can see this as a cut of the gradient chain, even if from construction we just had a solver that didn't provide a gradient, right? It's putting something into this graph which doesn't have a gradient, which cuts the forward chain. Inherently, we have a mismatch between our loss landscape and the gradients we're getting, right? So we're not actually integrating these gradients to yield the loss landscape that we're moving in, but we're getting different updates. So we have an inherent mismatch between landscape and the vector field for optimization. And interestingly, this causes a kind of rotation or rotational components, which are typically undesired and which you can correct with some additional methods that we looked at in this paper. But so this is an interesting side aspect. Important to keep in mind though is as soon as we mess with the gradient flow, we are dealing with a mismatch between gradients and energy landscape. And the central advantage, however, of this removal of the gradients, or basically working without a gradient for the solver, is that suddenly, instead of relying on a pure prediction, right? If you think of your solver, it doesn't have gradients, okay, we can only use it to produce data, then you're stuck with a prediction task, right? The network has to do everything. If you take the same network and let it work together with approximate solve, even if you don't have the gradients, that gives you this correction task. And in our paper, we ran all these versions for different models. So for KS and Kolmogorov and others, you can always now compare the full training for prediction and this truncated no gradient training for a correction task. And across hundreds of models, you can see substantial gains of accuracy, 4 to 5, sometimes even more, with an identical network. These gains are just there from switching from a prediction task, pure network prediction, to something that puts the solver into the loop, even if it doesn't have a gradient. So this is one of the most important takeaways also for me from this paper. The with gradient version really is the best thing to do. You get the most accurate models out of it, but nonetheless, if your solver does not have a gradient, nonetheless, it's really worth integrating the solver and starting to train with it. This already fundamentally improves the learning task and stabilizes training. So this is, I think, really an important takeaway message here. And it's even more important because what we noticed in our paper here is that the scaling is really not that great for neural networks. So instead of what you might be used to from numerical solvers, that they have an order of 1 or higher for the convergence of your solver. Instead, what we saw across the networks, and we had thousands of them literally in our study here, the scaling was surprisingly stable with only 1/3. So it's actually really bad, really bad scaling. It means when you double the size of your network, you're only getting 20% of improvement, roughly, out of it. Which means you would need to go to huge models to make them really accurate, or again, let's simplify the task. If you can work with a small network correction task, that you solve it to part of the job and then add a small network on top, that's going to be fast for the network, and you won't need a lot of weights to learn this residual of your solve. So another reason to basically to keep the networks as small as possible. It's actually also really important for generalization. I don't want to go into details here, but potentially now the solver, the P, can generalize to new cases and ideally reuse the correction that was learned from the neural network. Yeah, with that I want to come to a bit of an outlook. So there's also really interesting connections to diffusion models, which basically let you do uncertainty qualification topics. They can really powerful tool to deal with whole distributions of solutions. We also look at this for time stepping, inverse problems, and other things. So that's an interesting, mostly orthogonal topic that nonetheless nicely combines. We have another talk on this coming up. And with that, I want to wrap up a bit. So there's 3 main points that I hope you can actually take out of this talk despite all the details. So one is that the unrolling really improves training. Then it's really worth integrating your solver, going for these correction tasks. They fundamentally increase the accuracy instead of dealing with pure predictive tasks. So it's actually also, I think for many people in the field, this is a great message. You don't need to throw away the solvers, right? You can actually keep your solvers around, keep on using them, and augment them with neural network components to yield hybrid solvers. I think there are many really exciting questions for research left. And if you're interested, please also check out our website. Many larger updates in the pipeline here, but they already cover a lot of the basic topics of setting up these iterative solvers and the joint training. Of course, I also want to thank the PhD students and people from my lab who worked on these topics. Björn List, Patrick Schnell, Liwei Chen, and Georg Kohl produced these results. So please check out their papers, which are available online. And thanks for listening.